Over a 30-year mortgage, the average American homeowner spends $60,000 to $90,000 on heating. It feeds a $120 billion industry built on one requirement: you keep paying. 5 proven technologies offered another path: no fuel, no monthly bill, no service contract. Each one worked, each one still works today, and every one of them was quietly erased, not by conspiracy, but by something far more effective. In 1881, Edward S. Morse filed a patent for a device that could heat a home using only no fuel, sunlight, a dark surface, and simple convection. His patent drawings show a glazed box mounted on a south wall where sunlight passes through glass and warms a blackened metal plate. Air rises behind the plate, flows through vents, and delivers warmth directly into the living space. Morse's own field notes describe the results. On clear winter days, the outlet air reached temperatures between 120 and 150 degrees Fahrenheit, rivaling the supply from a small furnace. A century later, the same principle lives on in garages and workshops across the country. In Portland, Oregon, a homeowner built a solar air heater from crushed aluminum cans, a sheet of polycarbonate, and scrap lumber. The total cost was $37. The builder kept meticulous logs. On a bright January day, the panel delivered between 2,500 and 3,500 BTUs per hour, enough to heat a small room. Over the course of a single winter, the system cut the household's natural gas bill by 40%, dropping monthly costs from $120 to just over $100. No filter changes, no tune-ups, no scheduled replacement cycle. The collector ran quietly, day after day, for years. This is not an isolated experiment. Ford Motor Company retrofitted 7 North American factories with commercial solar air collectors in the late 1980s, saving more than $10 million in heating costs and reducing fossil fuel use by hundreds of thousands of BTUs each year. NASA tested solar air panels at its Langley Research Center and on remote Army bases, confirming outlet temperatures and heat output that matched Morse's original numbers. Across all these cases, the panels operated for 30 to 40 years with little more than a wipe down and the occasional replacement of glazing. But despite a track record that spans from the 19th century to modern corporate installations, solar air heating has vanished from mainstream home building. The reason is not a technical flaw. Building codes default to a standard furnace and require a UL listing for any heating equipment. UL test protocols are written for forced air, fuel-burning systems, not for passive solar collectors. Without a manufacturer's lobby to push for a dedicated standard, the solar air heater is classified as non-compliant, locked out of most new construction, and erased from trade school curricula. The result, a technology that can heat a room for pennies, is sidelined, while the business of recurring fuel and equipment sales rolls on. By 1940, more than 1 million American homes relied on solar water heaters, simple roof-mounted boxes lined with blackened copper pipe, sealed behind glass and plumbed to an insulated tank. The principle was as direct as it gets. Sunlight strikes the collector, water circulates through the dark piping, and the storage tank holds the day's warmth for evening use. In government tests, 1 square meter of collector surface could deliver about 450 British thermal units per hour, with water temperatures routinely reaching 130 to 160 degrees Fahrenheit. Seasonal performance factors, how much of the year's water heating comes from the sun, landed between 0.6 and 0.75, even in northern states. Durability was not a marketing claim, it was documented. The Quality Inn in Key West, Florida, installed a NASA-engineered solar water heater in 1977. The design was unremarkable by today's standards: 28 square meters of glazed collectors, copper serpentine piping, and 2 insulated steel tanks. But the service record is anything but ordinary. Over 47 years, the system required only 1 glass replacement and routine coil cleaning. No pumps, no control boards, no proprietary parts. The hotel's maintenance logs show 4 scheduled inspections and no major repairs. The original collector array still delivers hot water to guest rooms, outlasting 3 generations of gas-fired equipment in neighboring buildings. The cost story is just as stark. The quality-in system paid for itself in 2.5 years. Over its lifespan, it saved the hotel an estimated $450,000 in fuel costs. The price per gallon of hot water, averaged over decades, came in at 2 cents, less than a third of the national average for gas-fired heating. For homeowners, the math was even simpler. A black pipe collector could last 40 to 50 years with no monthly bill and no service contract. But the solar water heater's dominance did not survive the 1950s. As natural gas pipelines spread across the country, utilities rolled out contractor incentives and consumer rebates for gas-fired water heaters. Brochures promised instant heat and no fuss, while plumbers were paid bonuses to recommend gas over solar. Building codes and equipment standards followed suit, defaulting to tank-type water heaters and requiring UL listings that favored manufactured fuel-burning units. By the 1960s, solar water heating had been quietly erased from trade school curricula and new home specifications. The result? A technology proven to deliver decades of reliable, fuel-free hot water was sidelined, not because it failed, but because it did not feed the revenue streams of the modern heating industry. A rocket mass heater burns wood at temperatures that reach 1,800 degrees Fahrenheit, hotter than most industrial kilns. Instead of losing that heat up a chimney, the exhaust is routed through a long bench made of cob or stone. The mass absorbs the energy and radiates warmth for 12 to 18 hours after the fire goes out. A single batch of small diameter wood, twigs, branches, even construction scraps can keep a large room comfortable overnight. In measured trials, fuel use drops by 80 to 90% compared to a conventional wood stove. The Burlington Cooperative in Vermont put these numbers to the test. In 2021, residents built a rocket mass heater for their 3,000 square foot common area using about $45 worth of clay, sand, and salvaged brick. During the first winter, their wood consumption plummeted from over a ton to just 300 pounds of pellets. That is a 90% reduction. The heater's thermal bench stayed warm 14 hours after the last fire, holding steady through sub-zero nights. Logs from the project detail continuous output of 4 kilowatts, verified by surface thermometers and indoor temperature tracking. But the system ran into a wall. The International Residential Code requires all heating appliances to be UL listed, a process designed for manufactured mass-market equipment. The Burlington Group presented NASA technical data and performance logs to their city's building department, but the official response was blunt. Rocket mass heaters are not a listed device, and therefore cannot be approved for residential use. The code does not recognize the technology, no matter how safe or efficient it proves in the field. As a result, a device that can heat a home for decades, with no monthly bill and no service contract, is classified as non-compliant, not because it fails, but because it is not a product anyone can sell. In Phoenix, Arizona, a homeowner faced summer heat with a windcatcher tower, an ancient design first seen in Yazdi, Iran, around 1000 BCE. Rising above the roof, the 2-meter tower channels wind down a shaft where a silenced inlet and heat exchange core pre-cool incoming air. Over a scorching season, sensors tracked indoor temperatures averaging 15 to 20 degrees Fahrenheit cooler than a sealed, air-conditioned home. Airflow rates of 0.3 to 0.6 cubic meters per second kept rooms comfortable even as outside temperatures topped 110 degrees Fahrenheit. Cooling bills dropped by 25%. Yet local building code refused to recognize the system, citing no category for natural ventilation towers. Only after the homeowner submitted engineering data from Cardiff and Brunel University proving airflow and cooling did the city grant a variance. In Taos, New Mexico, a designer built with rammed earth. The home's 30-inch thick walls, with a heat capacity of 1.5 megajoules per cubic meter per Kelvin, absorb winter sunlight and release it at night, cutting temperature swings by 8 to 12 degrees. Department of Energy and NREL studies confirm adobe and rammed earth homes reduce annual heating energy by 40 to 70% compared to wood frame construction. Construction costs run about $30 per square foot, nearly half the price of modern stud walls. But the International Residential Code, focused on insulation R values, nearly blocked the project. Only Department of Energy research from the 1970s and a variance allowed it to proceed. Both cases show passive airflow and thermal mass deliver comfort, resilience, and energy savings, yet face regulatory barriers because they fall outside prescriptive, product-based standards. Today, the quiet efficiency of these sideline systems still outperforms most code-approved heating. Their absence from catalogs and classrooms isn't technical, it's economic. As fuel prices climb and supply chains strain, the true cost of compliance is paid by every homeowner. The choice to break that cycle starts now.